An extremum, plural extrema, is a maximum or minimum. Maximums are larger than other values. Minimums are smaller than other values. Local or relative extrema are for an open interval containing that point, thus cannot be at an endpoint, basically near that point. Global absolute extrema are for the whole domain or given domain, thus either in the interval or at endpoints. Extreme value theorem. A continuous function on a closed interval will have absolute extrema on that interval. Such extrema could occur multiple times. Fermat's theorem. If f has a local extrema at C, and if f prime of C exists, then f prime of C equals 0. A critical number of a function f is a number C in its domain of f such that either f prime of C equals 0 or f prime of C does not exist. Fermat's theorem. If f has a local extrema at C, then C is a critical number of f. Absolute extrema test. Since extrema are at either critical points or endpoints, we compare the values of the function there. The largest, or smallest, is the absolute maximum, or minimum. If on an infinite interval, then try to find local extrema that would eventually become global extrema. Here are some pictures. On the left, f prime goes from negative to 0 to positive, so the change of the first derivative is positive. That is, the derivative of the derivative, which is the second derivative, is positive. Here, f is increasing at an increasing rate, and with tangents below. Concave up, a U-shape, has f double prime greater than 0. Concave down, an N, has f double prime less than 0. An inflection point is where concavity changes. That is, second derivative changes sign. Note that concave up means the tangent lines yield under approximations. We'll note if f prime and f double prime are positive, negative, 0, or does not exist on these intervals. X less than 0, x equals 0, x greater than 0. Here is an example. For f equals x squared, the derivatives go from negative to 0 to positive when the intervals change from x less than 0 to x equals 0 to x greater than 0. Note that f double prime is always positive. For g equals absolute value x, the derivative goes from negative to not existing to positive when the intervals change from x less than 0 to x equals 0 to x greater than 0. The second derivative is omitted. Notes on how these upcoming slides are written. To keep the presentation concise, we'll limit counterexamples to the fewest and most basic ones that prove the point. Although other counterexamples exist, we'll omit them because these ones should be good enough. The logic of the statements is of utmost importance. Here are some examples. Can we tell if we have a max or min at a critical point, if prime equals 0 or does not exist? No. Both x squared and minus x squared have f prime of 0 equals 0, but we have a min and max. No. Both absolute value and negative absolute value have f prime of 0 does not exist, but we have a min and max. In fact, x cubed and minus x cubed have both f prime of 0 equals 0, but neither have a max or min. A sign change of the derivative at a critical point is decisive. Positive to negative is a max because we go up, then down. Negative to positive is a min because we go down, then up. Here are some examples. Can we tell if we have a max or min at f prime equals 0? No. Both x squared and minus x squared have f prime of 0 equals 0, but we have a min and max. If we have flatness from f prime equals 0, then the concavity from f double prime is decisive. Concave up from f double prime greater than 0 is a min because we're at the vertex of the U shape. Concave down from f double prime less than 0 is a max because we're at the vertex of the N shape. Note that f double prime equals 0 is not decisive since, for example, both x cubed and minus x cubed have f prime of 0 equals 0, and neither have a max or min. Here are some examples. Note that neither does f prime equals 0 nor f double prime equals 0 tell us anything if it's a max or min. Here's a picture. First derivative test. At a critical number, if f prime goes from positive to negative, then it's a local maximum, minus x squared. If f prime goes from negative to positive, then it's a local minimum, x squared. For maximums, we've increased all we can, and now we can only decrease. For minimums, we've decreased all we can, and now we can only increase. It is not simply f prime equals 0 or does not exist. Without checking a change of signs, we could have a maximum, a minimum, an inflection point, x cubed, or none. Consider a constant function. Use the first derivative test only when we can find if f prime is positive or negative to the left or right of a critical point. It works even regardless of f double prime. Here is a picture. Second derivative test. At f prime equals 0, if f double prime less than 0, then it's a local maximum, minus x squared. F double prime greater than 0, then it's a local minimum, x squared. When flatness occurs, we could have concave down for maximums and concave up for minimums. It is not simply f prime equals 0, because if f double prime equals 0, it could be a maximum, minus x to the power 4, a minimum, x to the power 4, an inflection point, x to the power 3, or none. Consider a constant function. The sign of f double prime must be strictly greater or less than 0. Use this test if we can't find positive negative nature of f prime to the left or right of a critical point, but have f prime equals 0 and a way of finding the positive negative nature of f double prime. To sketch, we first need to know what graphically happens when f prime, and f double prime is 0, positive, or negative. Negative, 0, positive. F value below x-axis, on x-axis, above x-axis. F prime slope, decreasing, flat or constant, increasing. F double prime concavity, N shape, 0, a U shape. To sketch f of x equals x cubed plus 3x squared, we first find the intervals where f prime, and f double prime are 0, positive, and negative. F of x, f prime of x, f double prime of x. Now we can interpret graphically what happens when f prime, and f double prime is 0, positive, or negative on those intervals. Here's a diagram. Now we start sketching in this order. Regarding f, we point out the zeros on the x-axis and then section out regions above and below the x-axis. Regarding f prime, we draw a curve that is decreasing or increasing, depending on the region, and then flats for the zeros. Regarding f double prime, we smooth out the curve so that there is a general N shape or U shape depending on the region. Regarding f, we point out the zeros on the x-axis and then section out regions above and below the x-axis. Regarding f prime, we draw a curve that is decreasing or increasing depending on the region and then flat for the zeros. Regarding f double prime, we smooth out the curve so that there is a general N shape or U shape depending on the region. Here's a picture. We can get the general shape of the curve, but the only values that we truly know are x-axis intercepts, where f of x equals 0, explicitly -3, 0, and 0, 0. Note that f seems to have a local maximum at x equals -2, an inflection point at x equals -1, a local minimum at x equals 0. We can prove this by returning to the chart with the intervals where f, f prime, and f double prime are 0, positive, and negative. Here are the values. First derivative test. Regarding f prime, note the following positive negative changes of sign. At x equals -2, we go positive to negative. This is a maximum since we go up then down. At x equals 0, we go negative to positive. This is a minimum since we go down then up. Second derivative test. When we're flat, that is f prime equals 0, note the positive negative sign of f double prime. At x equals -2, f double prime less than 0. This is a maximum since we're concave down and flat. At x equals 2, f double prime is greater than 0. This is a minimum since we're concave up and flat. Inflection points. Where does f double prime change sign? At x equals -1. Here's a picture. Evaluating f at these values of x, we get these important points. X-intercepts of -3, 0, and 0, 0, and y-intercept of 0, 0. Relative maximum of -2, 4, and relative minimum of 0, 0. Inflection point at -1, 2. Here's the picture. Now, let's restrict our domain to -3.1, 1.1. Based upon the candidate test, what would be the absolute maximum and minimum? For the candidate test, we evaluate f at the critical points, f prime equals 0 or does not exist, and at the endpoints. On the interval -3.1 to 1.1, note the following. The absolute minimum is this and occurs at x equals -3.1. The absolute maximum is this and occurs at x equals 1.1. Mean value theorem for derivatives. Let f be a function that satisfies the following hypotheses. F is continuous on the closed interval ab. F is differentiable on the open interval ab. Then there is a number c in ab such that this tangent line slope equals secant line slope. Rolle's theorem. In addition to the mean value theorem, if f of a equals f of b, then the secant line slope is 0, and so there is a horizontal tangent. Consider f of x equals x squared. On 0, 2, The mean value theorem shows that f prime of a equals 2 for some a in 0, 2, since we have this. On minus 2, 2, Wills' theorem shows that f prime of b equals 0 for b in negative 2, 2, since we have this. We have three existence theorems that prove a point exists if the requirements are fulfilled, but we don't know that point explicitly. The intermediate value theorem regarding values, if there is continuity. The extreme value theorem regarding absolute extrema, if there is continuity and a closed interval. The mean value theorem regarding derivatives, if there's differentiability. A rectangle has a perimeter of 20 units. What are the side lengths of the rectangle that has the largest area? We have two equations and two unknowns. Area, perimeter. We want to maximize the area function, but we can't do it directly since it is in terms of two variables. So we have to solve our perimeter function for one variable and then substitute it into the area function. That way, we would have the area function in terms of one variable. Let's solve for b. Mathematically, it doesn't matter which variable, but it might matter which one when solving by hand. If we solve for b, we get this, and we have to note its domain is this. Although we get degenerate rectangles, that is lines at the endpoints, we still need the endpoints. And so the area function and its derivatives become this. Note that the critical points when a prime of h equals 0 does not exist is when h equals 5. To find the absolute extrema, we evaluate a of h equals 10h minus h squared at its possible candidates, that is, the critical points and endpoints. A of 0 equals 0, a of 5 equals 25, a of 10 equals 10. The largest of the values is the absolute maximum, and smallest for minimum. For us, it means that a rectangle with a perimeter of 20 has a maximum area of 25 with side lengths of 5. Now, in some cases, we could analyze the first derivatives to find relative extrema that could eventually become absolute extrema. Consider finding the maximum area by applying the first derivative test. We have the following. Note that the relative maximum at h equals 5 becomes an absolute maximum. A prime of h greater than 0 for h less than 5, and a prime of h less than 0 for h greater than 5. By similar logic, an absolute minimum would have f prime changing from negative to positive at its critical point. A circle's area is increasing at a rate of 18 pi square units per second. When the area of the circle is 9 pi square units, how fast is its radius increasing? In a static situation, the area relies only on the radius. However, in a dynamic situation, the area eventually relies on the time. Note that in differentiating our dynamic situation, we need chain rule. Static, dynamic, differentiate with respect to t. Here, we used chain rule. In other questions, we might need quotient rule, product rule, etc. Also, in other questions, there might be more variables, but only certain ones might change with respect to time. Now, after differentiation, we can start replacing values that we know or could solve for. We have the following. Note, although we solved r prime of t equals 3, we don't actually know what t is. Here are other examples of how differentiation is done in related rate questions. Cones, similar triangles.